You're surrounded by this invisible language, spoken 24/7 by the phone in your pocket and the towers you see on the skyline. So today, we're going to decode that secret language of antennas, breaking down their complex invisible world into something we can all understand. We're going to dive into the fundamental rules that decide how these signals travel, powering everything from our phone calls to the satellites orbiting way above our heads. It's literally the invisible architecture of our modern lives. All right, to understand this language, we have to start with the first and most important rule of all, this surprising principle of two-way communication that is the foundation for everything antennas do.
It's a question a lot of people ask, and you might think the answer is super complicated, right? But the truth is, the principle behind it is surprisingly simple and pretty elegant too. It's this core idea called reciprocity, and really all it means is this. If you know how an antenna speaks, you automatically know how it listens. Its characteristics, like its gain and its polarization, are identical in both directions. Simple as that. A good transmitter is a good receiver. Okay, so if an antenna speaks and listens the same way, we need to understand the shape of its voice. And in the world of radio waves, this shape has a name: polarization. Now, that sounds a little technical, but stick with me here. Polarization is basically just the direction a radio wave wobbles as it travels through space. Is it oscillating up and down or side to side? The answer comes directly from the physical orientation of the part of the antenna that actually sends out the wave.
So for instance, if that radiating element is positioned vertically, standing up straight, it creates a vertically polarized wave, one that moves up and down as it travels. And as you've probably guessed, if you turn that same antenna on its side, making it horizontal, it creates a horizontally polarized wave that moves side to side. Makes sense, right? But here's where it gets really cool. What if you combine both? Well, then you get something called circular polarization, where the signal literally spirals through the air like a corkscrew. And this is absolutely critical for things like satellite communications, where the orientation between the transmitter on the ground and the receiver in space is constantly changing. Okay, so we've got the signal shape down. Now let's talk about its direction, its focus. And that's a property we call gain. A basic antenna is a lot like a bare light bulb. It just radiates its energy in all directions, more or less equally. We call that an omnidirectional pattern. But the problem is that energy gets weaker very quickly as you move away from it because it's spread so thin. And this is a super important point. Gain isn't about creating more power out of thin air. It's all about taking the power you already have and focusing it. It's the difference between that bare light bulb and a powerful spotlight. And here you can see what that focus looks like. Instead of spreading out everywhere, the energy is concentrated into a powerful main beam pointing in a very specific direction. Those smaller bumps you see, those are called side lobes. They're just small, unavoidable bits of energy leaking out in other directions. So we've covered the signal's shape, its polarization, and its focus, its gain. But so what? Why are these concepts so critical in the real world? Well, the answer is all about efficiency. It comes down to avoiding a massive and totally avoidable loss of energy if you get it wrong. Get this, mismatching the polarization between the two antennas, a problem called cross-polarization, can cause you to lose up to 90% of the signal's energy. I mean, that's the difference between a crystal clear connection and one that drops completely. It's like trying to catch water with a net. Most of it just passes right through. And gain is just as crucial. A high-gain antenna acts like a telephoto lens, but for radio waves. It lets you zoom in on the signal you want, while attenuating or weakening all the noise and interference coming from other directions. It makes that one important signal really pop. We've talked about focusing energy with gain and losing it with bad polarization. But how do engineers actually measure these invisible forces with any kind of precision? Well, they use a unit called the decibel, or dB. It's a logarithmic scale, which sounds complicated, but it's really just a clever way to handle the huge swings in signal power without having to write out numbers with like a dozen zeros. You're already familiar with decibels for sound. You know, a jump from a 70 dB conversation to a 120 dB jet engine is a massive change. That's because a small increase on the decibel scale represents a huge jump in actual energy. It works the exact same way for radio signals, and it's why your Wi-Fi signal can go from excellent to poor over just a few feet. All these principles, polarization, gain, how we measure it, all come together in the technology we see every single day. Take this cell tower. It uses what are called sector antennas. They're high gain, they're directional, and they're arranged to efficiently focus signals right where they're needed most, giving us 360-degree coverage without wasting energy. So really, the key takeaway is that this seemingly secret language, which is built on just a few simple rules, is what allows for the incredibly complex web of wireless communication that we all rely on every single day.
And this brings us to one last really interesting thought. We've seen how antennas are designed with these fixed patterns. But what happens when smart antennas can actively learn, adapt, and steer their beams in real time to find the best signal? What new possibilities open up when they can truly master this invisible language, all on their own?